Welcome to this FMSP online revision session. The session today is looking at the MEI D2 specification, and the topic is logic and Boolean algebra. So looking at logic and Boolean algebra, what do we need to know? The specification says that you need to know and understand how to form compound propositions by using the connectives there. So propositions are statements that can be either true or false, and compound propositions are formed using a combination of statements and connectives. We call these logical operators. You also have to be able to use truth tables to analyze propositions, and truth tables we use ones and zeros to represent true and false. You have to be able to manipulate Boolean algebra expressions using the laws of Boolean algebra. And to be able to model compound propositions using circuits. So let's have a look at some questions and see how it comes out. First of all, a few things. The Boolean variables we tend to use just little letters for, P and Q or ABC. The connectives that we need are not, and or, and they look a little bit like things that you get in set theory if you've done any. So not, for which we use a kind of squiggle, is a little bit like the complement, and, which I always think of as a hat, is like an intersection, and or, which is an upside down hat, I guess, is like a union. And as I said before, we use 1 to represent true, 0 to represent false. You also need to understand the arrow there that implies that, and if we put it the other way round, it's is implied by, and if you've got double arrow ahead like that, it works in both directions, so that's if and only if. These are our basic truth tables. So the truth table for not, and, or, implies, implied by, and equivalence are all things that you need to know so that you can fill in the tables in the questions. Similarly, you need to know and understand the basic laws of Boolean algebra, which look a bit confusing but are no different from the normal laws of algebra in most cases. The names here, complement, double negation, distributive, associative, De Morgan's, if you can't remember those, that's not the end of the world, although it's quite a good idea to say what you're doing, but if you can't remember the names, don't worry too much about it. So here's a question from a little while ago. Starts off with something in words that we have to comment on, and that's fairly normal in these cases. Then it involves drawing a truth table and using some Boolean algebra, and if it says use Boolean algebra, you must not use a truth table. You won't get any marks for using a truth table. So first of all, an old joke, if it moves, salute it, and if it doesn't move, paint it. And you have to assume that the instructions are carried out completely in some kind of local universe, some foreign planet. So everything that doesn't move has been painted. First of all, a recruit answers something which hasn't been painted. What should he do and why? And the and why is really important because there are 3 marks for this. So they're wanting something more than a paint it or don't paint it answer. So here we are, something that isn't painted. Well, if it isn't painted, then it must have been moving. So therefore he should salute it. And we have to say that if it's not painted, it must have been moving. So there we are, I've written an answer, something along those lines is absolutely fine. I've said what you should do and I've given a reason. The second part, we encounter something which is painted. Do we know what to do? Justify our answer. Well, if it hasn't been painted, if it has been painted, then it wasn't moving. But just because it wasn't moving when the guys came along with the paint doesn't mean that it couldn't move. So in this case, the answer is we don't know what to do. Okay, sorry about the long silence there, but there we are. I've written my sentence now. We don't know. It wasn't moving when it was painted, but that doesn't mean that it can't move, so we don't know. And that's a little bit counterintuitive, I think, perhaps. And there's the mark scheme. So 1 mark in each case for saying correctly what you should do, that you should salute it and that you don't know. And then 2 marks for giving the reason, and those have been split into an M1 and an A1. So an M1 is you had a go at giving a reasonable explanation, and A1 is it was precise enough to get the complete mark. And there's what the examiner thought you should say. Right, the next part involves a truth table. And what I've done here is I have drawn the truth table. Now this is called a nested truth table, where I've literally written out the proposition in the table with the brackets showing so that I can fill it in below. And I think this is probably the easiest way to do this. Now when you do truth tables, you kind of need to do them in order. So first of all, you look at it and you say, how many variables do we have? We've got M, we've got S, and we've got P. So 3 variables. We need to have 8 rows. The little examples I gave you before, which I've put at the side here, had 2 variables, 4 rows, but 3 variables needs 8 rows. Then we can start by filling in some 1s and 0s. So our first variable is M. So what I'm going to do with M is I'm going to put 4 situations where we've got a 1, and 4 where we've got a 0. Then when I get to S, I'm going to have 2 and 2 and 2 and 2. So I've got the same number of 1s and 0s, but I'm making sure that the 1s and 0s are all in different positions. And finally with the P, that's going to be 1 0 1 0 all the way down. And I notice I've got an S at the end here, so I can fill this one in with my S variables. And that's the first stage, if you like, of the solution. Now, I think that if I try and change my ink colour so that you can see the second stage clearly, the second stage is to look at the first layer of brackets. So this one here and this one here. But before I do that, I notice that I've got a not M in here. So let's start by putting my not M's in. If it's not, it's the opposite way round. So that's going to be 0, 0, 0, 0 and 1, 1, 1, 1. Then I can start looking at the ways that we connect them together. So here I've got implies, M implies S. The way to remember implies is that it's all 1s unless you've got 1 and 0. Everything else is a 1. So 1, 1 is a 1, that's a 1, but the 1s and 0s are both going to be 0 and all the rests will be 1. Then I've got another bracket here that I can do. And again it's an implies, so 0, 1 is a 1, 0, 0 is a 1, Those are all going to be 1s. And this is the situation where it's a 0. So I've completed the 2 inner brackets now. And the next thing I'm going to do is look at the connective that gets those brackets together. So that's my AND connective there. So I'm going to change my colour again just to make it clear for you to see. Unfortunately, you can't do this in the examination, so you mustn't change colour in the exam. But having some way of sort of sorting it out in your head is very helpful. So what this is going to be is combining those 2 there to give me this column here. So AND is a 1 only if they're both 1s, and all the rest are 0s. So I've got a 1 and a 1 giving me a 1, and another 1 and a 1 giving me a 1. Then I've got some 0s, so I know that's going to be 0. That's a 1 and a 1 and a 0, a 1 and a 1, and a 1 and a 0. Now I've completed the first part of the statement that involved those first brackets and the second brackets. So now I can look at the AND with the not P here. And I didn't fill in the not P to start with, so I shall fill in the not P now. Try and get my ink again. So not P is, to remind you, it's just the opposite of P. So 0s instead of 1s, 1s instead of 0s. Then I can go for that AND again. So I've got this one here and this one here. So it's that one and that one to give me this one. This is the hardest thing, is keeping track of your columns. So with AND, we've got a 1 and a 0 is going to be a 0. A 1 and a 1 is going to be a 1. Then 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. So all of those. And now finally I can get to my last column in the truth table, which is the one where we come up with some kind of a conclusion, hopefully, and we are looking here at the AND there and the S there and saying, what do we get if we have implies that? And again, implies is only a 0 if we've got a 1 followed by a 0. So 0, 1 is 1, 1, 1 is 1, 2 zeros are 1, and all of these start with a 0, so they're all going to be 1. And because they are all 1, we have shown that the statement is true in all cases. So that's completed the that question. If we have a quick look at the mark scheme over here, then what we've got here is a beautiful copy of what I just did. You see, you get a lot of marks for this, but the first mark is the M mark. Now all of these A marks depend on the M mark. So if you don't get that M mark, you won't get any of the following 5 marks, and that's a really important thing to remember, because that M mark is for trying to draw a table with 8 rows. And as long as you've got your 8 rows and some variables up at the top, you will get your M mark. And then there is a mark for the M implies S column there, a mark for the not M implies P column there, a mark for that and, a mark for that and then 1 mark for getting the result correct. So that's pretty straightforward. And most people do answer these questions quite nicely, I must say. Right, then we get to the Boolean algebra. So here you are given 2 rules. And this first rule particularly is something that's called the contrapositive, and it's quite important, but it's not really covered very well in the textbook. It's only mentioned in a footnote on page 109. But basically the contrapositive says if you've got A implies B, then not B must imply A. And that's as stated up there. So looking at the statement here that we're being asked to prove, I think the first thing that you need to do here is you need to spot that there's going to be a contrapositive in it somewhere. And the contrapositive to me looks like we've got something going on with P's and not P's here. So the first thing I would want to do in this is to do some rewriting of the left hand side. So take the left hand side and I'm going to reorder it. So I'm going to write it as not P and not M implies P, and then and M implies S. And it's perfectly okay to do that reordering, rearranging, so that I get it in a way that looks more user-friendly to me. Then from that, if I now use the contrapositive, if I leave my not P there and not M implies P, I could rewrite that as not P implies M. And I've used the contrapositive rule in that if both of the variables become not what they were before, then we can swap the order on the implies sign. So not M becomes not M, which is M, and P becomes not P. So what I've used there is I've used the contrapositive. And now we've got not P and not P implies M. Well, if you look up here, X and X implies Y is the same as just Y. So not P and not P implies M is going to be the same as just M. And similarly up here again, only this time we've got M and M implies S, so that's going to be just the same as S, which is our right hand side. So by using the two rules up there, we've managed to prove that statement using Boolean algebra, and it's not so bad. Looking at the mark scheme here, you'll see that there's a method mark, and the method mark is for basically having a go, and that having a go would be the reordering here. Have you tried to reorder it in a way that enables you to use the two rules that you were given? And then picking up on the contrapositive, getting the reordering correct gets you 1 accuracy mark, picking up the contrapositive, and then there's a mark at the end for using that other rule, which is called modus ponens, but you don't need to worry about that. Nobody's going to ask you to remember that. That's the summary of what modus ponens means, but don't worry about it. Right, the examiner's comments for this question. So most of the candidates were able to answer part 1 correctly. With the that was the one where we had to salute it, but actually struggled with that second part because they weren't quite sure how to give the correct argument. And my recommendation is honestly just try to write down how you reason it out in your own head. You don't have to write it in fancy language. Truth table was done well. A few odd slips, that's all. And in the last part, not done so well. And I think this is generally the case, that truth tables are done well and the Boolean algebra many people find much harder. So try and make sure that you get some practice in on Boolean algebra before you go into the exam. Right, the next thing, the other part I suppose of this, is switching circuits and logic gates. And these questions are, in all honesty, less common, but we still need to cover one. You need to be aware of the difference between a switching circuit, which is just putting switches in series, and a combinatorial circuit, which uses these symbols for the logic gates. And those are the most common ones. You might encounter those there. So your switching circuit looks like this, just variables connected by lines, and the combinatorial circuit will use those logic gates to combine things, but they are equivalent ways of showing the same information. So here's a question. This is quite an old question, but it's the only long question I could find that had a lot of this in, so we won't attempt to read it all at once. Here we go. This is the first part. This is a switching circuit for a car, so S for side lights, H for headlights, and S, A and H and F for fog lights. Don't worry about ganged switches. That doesn't help you. It just says describe in words the conditions under which the fog lights will come on. So there's the fog lights. It's S and H and F. So all we have to write down is fog lights on if the side lights and headlights are on and the fog lights on. So F is the high intensity rear fog lights, and if they come on, then we've got fog lights on. So we need all three of them, and basically that's all you had to say. It was reading literally what it says on the diagram here. 2 marks for that. Just 2 marks. 1 for side lights and headlights, 1 for mentioning fog lights. Then the next part involves a combinatorial circuit. So it says write the output in terms of a Boolean expression involving S, H and F. So a Boolean expression is the one just using connectives, so we have to look at what we've got here, and we've got S followed by a not, we've got H followed by a not, and they're connected together by that symbol there, which is an OR symbol. So let's start off by saying not S or not H. And then there's another not here. So all of that has to have a not in front of it. So not S or not H. And then we've got F down here being combined with that and an AND symbol. So it's AND F. And it is literally a case of reading off the diagram, going through one thing at a time and making sure that you've incorporated everything. The next part of this question involved using a truth table, and I'm not going to draw the truth table again because they're quite time consuming. We've been through a truth table example, but in this case it was a truth table to prove that that was the same as that, and you had to put all of this in and all of this in and get the line in the middle. And again, this is how it was marked. This was quite a stingy marking because there was only 3 marks for it, and again the method mark, the one that enables you to get the other marks, was for the 8 rows, and then 1 for each side because they weren't considered to be very difficult. Right, here we go. Second part. The car's first gear can be engaged G if either both the road speed is low, R, and the clutch is depressed, D, or if the road speed is low and the engine speed is a correct multiple of the road speed. Draw a switching circuit. It's not as bad as it looks. We've got several variables going on here. G is going to be our output, so we'll worry about that in a minute. First of all, road speed low and clutch depressed. So that's definitely going to be R and D. And then or R and M. So basically we've got two situations here, either or, either R and D or R and M will give us the desired output, which was G. And that's all there is to it. Then, goes on a bit, doesn't it? We have to draw a combinatorial circuit to represent this expression here. So, drawing a combinatorial circuit. First of all, we've got four inputs, R, D, M and G. So let's start by putting those in. R, D, M, G. And then, as with any sort of algebra, start with what's in the bracket, and that's D or M. So I'm going to start by putting D and M and connecting them with that symbol for OR. Sorry, that's not very tidy, but in the exam that would be perfectly recognizable. Then we've got R and D or M. So I'm bringing R in and my output from the D or M and connecting those with an AND. And finally I've got AND G, so G comes along with the output from that, and they combine together with another AND symbol, and that gives us an output. So again, just simply by reading and following the basic rules, do the brackets first and so forth, it's not that tricky to do. The last two parts of this question were using Boolean Algebra, which we've covered something of already, and drawing another switching circuit. So if we just have a quick look at the mark scheme for this, there's our Boolean, our combinatorial circuit for the Boolean expression. M1 again for drawing something that is a Boolean expression with four inputs. So that's important. To get that M, you'd need the four inputs and you need it to be combinatorial. And then there's one mark for the first OR, one mark for the first AND, and one mark for the second AND. And a spelling mistake on the mark scheme. And then, not working through all of these because we've done them, but just so that you can see what has been done with the Boolean Algebra here, taking the expression and using the associative rules to actually squash down the right hand side, so taking R out as a common factor effectively, and then using the distributive rule just to do a bit of rejigging there so that it looks correct. And there's only 2 marks for that. And finally another switching circuit at the end, which is very similar to the first one. 1 mark. And answered well. Only part 3 caused any difficulties, where part 3, if you remember back that far, was the one involving the Boolean expression. So again, it's the Boolean algebra that catches people out. So that completes this recording. Hope you will have found it useful, and good luck in the exams.